The year is 2008, and something unusual starts happening in courtrooms across Germany and the United States. The court filings contain extraordinary claims. The black holes that will be created will spiral out of control and devour our planet within hours. These experiments must be stopped immediately.
Some of you might remember this. The defendants? The scientists working at the Large Hadron Collider, housed at the CERN laboratory in Geneva, Switzerland, which had just begun operations that September.
At the time, people around the world were genuinely discussing this possibility. They were truly afraid. And honestly, can you blame them? The idea that Earth could suddenly be swallowed by a black hole is a terrifying scenario, isn't it? It's the kind of scenario you barely even see in science fiction movies. And of course, conspiracy theorists had a field day, pumping up this fear, just like they do today with 5G and similar technological developments.
Now, here are the facts. Are scientists trying to create black holes in the Large Hadron Collider? Yes. Is it possible? Yes.
Could a large black hole formed on Earth swallow our entire planet? Absolutely. But here's the thing. It doesn't work like that. Let's talk about it. But before we tackle that question, let's pick up where we left off at the end of our last video. Remember, it took scientists decades to finally accept the existence of black holes. Decades of saying, okay, fine, something like this must exist.
And now black holes have become everyday general knowledge. So commonplace, in fact, that people are filing lawsuits about them in court. So, how did we get here? And where are we going?
The secret hero who brought us to this point comes this time from Japan. His name, Minoru Oda.
In the 1960s, Minoru Oda, a young physicist working at MIT, joined forces with the research team there to launch a rocket carrying the most advanced imaging equipment of the era into space.
The legendary experimental physicist Bruno Rossi was leading this team.
The instruments aboard this rocket observed X-rays and gamma rays streaming in from celestial objects across the cosmos. This had to be done from a rocket because Earth's atmosphere and magnetic field scatter and absorb the X-rays and gamma rays before they can reach us on the surface. The team expected to detect X-rays similar to those coming from our sun, but when the results came in, they were stunned. Some of the X-rays and gamma rays they captured were extraordinarily powerful, far more intense than anything they'd anticipated.
But their equipment couldn't tell them exactly where these rays were coming from. They could only narrow it down to a very broad region of the sky.
Within that region lay the constellation Cygnus, the Swan. But which specific stars within that constellation were producing these extraordinary rays remained a complete mystery. After completing his assignment and returning to Japan, Minoru Oda set out to solve this problem on his own. He developed an entirely new solution. He called his invention a modulation collimator, a device that could pinpoint the exact location of incoming rays with far greater precision.
But there was a problem, a big problem. In 1960s Japan, there was no rocket capable of launching his device into space.
But instead of giving up, Oda improvised. He attached his instrument to a weather balloon, the kind used in meteorology, and sent it soaring 30 kilometers up to the very edge of space.
Each time, the instrument would parachute down, landing in mountains or seas, and somehow they'd find it and bring it back every single time. They kept this up for 4 years.
And the results they gathered kept narrowing down the region where those X-rays were coming from. But they noticed something strange. In the area where this incredibly powerful source should be, there was nothing visible. No star, no formation, nothing that could explain such intense X-ray emissions.
Oda's tireless work and determination caught the attention of the Americans. In 1970, the world's first X-ray detection satellite, named Uhuru, was launched into orbit. And of course, Minoru Oda was part of the team. The Uhuru satellite narrowed down the source of those X-rays from the Cygnus constellation even further. And in 1971, the source was finally identified. Minoru Oda's quest, 7 years in the making, was complete. At the source of those rays, they found a massive blue giant star, 30 times the mass of our sun.
But when they studied this star more closely, they made an absolutely wild discovery. Analysis of the light from this blue giant revealed that it was orbiting something else, completing a full cycle every 5.6 days.
For a star this massive to complete an orbit that quickly, the object it was orbiting had to be enormous. When they calculated its theoretical mass, whatever was there had to be at least 10 times more massive than our sun. But here's where it gets deeply unsettling. This other massive object, the thing pulling the blue giant around, wasn't bare. It was invisible, completely impossible. A giant star orbiting something you cannot see. This was nothing other than a black hole. The first black hole ever detected through observation in the history of humanity was staring right back at us. And it needed a name: Cygnus X-1. Meanwhile, before it was officially confirmed to be a black hole, theoretical physicist Kip Thorne entered into a written bet with his close friend, fellow theoretical physicist Stephen Hawking. Kip Thorne was convinced from the early evidence that this was absolutely a black hole. But Hawking argued that the calculated mass of this object fell below what we call the Chandrasekhar limit, the critical threshold a star needs to exceed in order to collapse into a black hole. The stakes of the bet? Magazine subscriptions. And as you might have guessed, Stephen Hawking lost.
But this wouldn't be Hawking's last bet. Later, he'd team up with Kip Thorne to enter another wager against John Preskill. But we'll get to that story another time. Stephen Hawking truly made science fun. But let's return to Minoru Oda for a moment. His years of relentless work with extremely limited resources would ultimately end a scientific debate that had lasted more than 50 years. In the years that followed, Japan launched its own space research program, sending countless rockets to study X-rays and explore the depths of the universe. These research programs became one of the driving forces behind Japan's transformation as a nation, all sparked by a single person's effort. There's so much to learn from Oda's story, both personally and as a society. But now, we had our proof. We found our first black hole. And in the years that followed, dozens, then hundreds more. With every spacecraft we sent, everywhere we looked, we started finding black holes. Billions of them in the universe. And not just any black holes, absolutely enormous ones, incomprehensibly massive.
Supermassive, hypermassive, containing millions of solar masses within them. Billions of these cosmic monsters scattered across the universe.
Then, in 2019, through a project called the EventHorizon telescope, which essentially turned our entire planet into one giant telescope, we captured an actual photograph of a black hole's event horizon in the Messier 87 galaxy, a black hole 6.5 billion times more massive than our sun. But do you know what one of the clearest truths we learned from all of this research was? No matter where you look in the universe, no matter which galaxy you examine, spiral, elliptical, any major galaxy, at the center, there is always a black hole. Every galaxy has a black hole at its center, and most of the time, it's a supermassive one.
In other words, a black hole that actually creates the entire galaxy. The most chaotic, the most extreme, the most bizarre structures in the universe that we still don't fully understand. These are the things that create everything.
How about a little speculation? What if, just what if, the Big Bang itself was actually a supernova in another universe?
But let's return to reality. What actually is a black hole? What's inside one? What's happening in there?
At this point, I have to bring up Einstein again. I really do. It's not intentional, but you simply can't explain these things without him getting involved. What I'm going to talk about here are Einstein's general relativity equations. These are the tools we'll use to understand a black hole. Or rather, these are the tools that are being used right now.
Friends, Einstein's general relativity equations are so elegant, so beautiful, that let me show you what Andrew Hamilton from the University of Colorado did with them. Because the equations are written with remarkably clean, comprehensible mathematics, think of them like a programming language. You can translate them into computer code and calculate exactly how much any object warps spacetime with incredible precision.
Andrew Hamilton took these equations and, using a 3D simulation program, calculated the warping caused by a black hole with extraordinary precision.
And the result that emerged was deeply strange. Let me show you. This is one of the black holes Hamilton's program produced. When you look at the event horizon, the bright ring of light surrounding it, the dark region, the part that looks like empty space, actually resembles a sphere, just like a planet. Then Hamilton drew meridians and parallels on this sphere, just like the latitude and longitude lines on Earth. And the result was shocking.
It looks like a sphere, like a planet, but there's something deeply wrong. The North and South poles appear right next to each other, an impossibly warped planet, like an illusion.
And here's something even stranger. In this simulation, when you throw something at the black hole doesn't swallow it. Strange, right? That's the real issue here. Black holes don't actually swallow anything. There's no swallowing at all.
It gets even stranger. The object you throw at the black hole doesn't speed up as it falls in. The opposite. It slows down, keeps slowing down, more and more.
And when it reaches the event horizon, do you know what happens? It stops. Yes, it just stops right there. Because at the event horizon, time stops.
This is the boundary of general relativity, the boundary of gravity, of all physics, the boundary of the universe itself, the event horizon, the place where time stops. But this is where the real problem begins. Time stops for us at that point. From our perspective, it stops. But what happens to that object after that? Where does it go? It doesn't necessarily stay there forever. But what happens to it, we simply don't know. But we do have an idea. Or rather, someone had an idea. Stephen Hawking. One of the most impenetrable and important paradoxes in all of history. The black hole information paradox.
Remember we talked about the gap between quantum mechanics and general relativity in our previous video? Well, the answer to this paradox is one of the strongest candidates to finally bridge that gap. Remember we talked about the gap between quantum mechanics and general relativity in our previous video? Well, The answer to this paradox is one of the strongest candidates to finally bridge that gap. But this paradox deserves its own dedicated video.
Now, let's circle back to that terrifying scenario we started with and quickly explain why that fear was completely unfounded.
At the CERN laboratories, they're not trying to create a black hole. They're trying to create tiny black holes, and for exactly the reason I just explained. Scientists believe the particles that cause these black holes go somewhere. But where? To another dimension. But which dimension? What number dimension?
In other words, it's theorized that black holes could be gateways to other dimensions. Wormholes, white holes.
There hasn't been progress on that front yet, but these tiny, minuscule things called quantum black holes are nothing to be afraid of because they are incredibly small and they exist for such an impossibly brief moment before vanishing that you'd barely know they were there. That's actually the challenge. Besides, every single day, countless gamma rays and X-rays are striking Earth's atmosphere and magnetosphere. And at the edge of space, when they collide with other particles, thousands of these quantum black holes are being formed and vanishing instantly.
And since we're all still here,
there's nothing to worry about. Don't worry.
In summary, black holes, the things we thought of as centers of chaos, are actually the source of galaxies, solar systems, and planets.
The keys to a universe born from the unknown. We don't yet know what lies beyond black holes, but we should be grateful for everything that happens on this side of them.
At the same time, black holes are like a doorway for us, a gateway opening up to a whole universe of new topics to explore.
The information paradox, multiple dimensions, wormholes, and so much more. Stay tuned so you don't miss any of it.
And I want to thank you, my supporters, once again. I'm counting on your support as we continue walking this path of scientific discovery together.
But no matter what, as always, until we meet again, I'm so glad you exist. Sending love.